All right, hello everybody. In this video, we're going to be going with hashing runtimes, which is the third question. Now, this question is going to test us on two different concepts, right? It's first of all going to test us on our understanding of singularly linked lists and arrays and how they function, but it's also going to test us on our ability to understand asymptotics, right? And so in order to better tackle this question, let's first of all start by going over a quick recap of how asymptotics work. Asymptotic analysis is a method of describing the runtime of an algorithm with respect to the size of its input, right? And so there are three main bounds that we have to know. The first one is omega bound. Omega bound is a lower bound on runtime in terms of input size, which means that as n goes to infinity, the runtime will never be faster than this bound. So if we look at this graph right here, if the runtime is n squared, as denoted by this blue line, then a valid omega bound would be this red line, which is equal to n, right? Because as n goes to infinity, n is always going to be less than n squared. On the other side of the coin is big O. Big O is the upper bound on runtime in terms of input size. And as the runtime will never be slower than this bound as they go to infinity. So once again, if this blue line represents n squared and this red line represents n cubed, then as you can see, as n goes to infinity, n cubed is always going to be greater than n squared. And so that's why n cubed can be considered a big O of a function with runtime n squared. Theta bound is a bit tricky because theta bound can sometimes not exist. We said that theta bound exists when O and omega bound have the same tightest bound, right? And so if O and omega bound close together, then theta bound exists. We can take a look at this function right here, right? Array iterator takes an integer array A, and we use this for loop to iterate through every single value in this array, in this A array, right? And for every single value, we're going to do system.out.println high. And as you can see, no matter what integer array A we put here, this function will always have a runtime of n, where n is equal to the length of the array, right? And so therefore, the O and omega are both equal to n in their tightest bounds. And so overall, we can say that this function has a theta bound of n. There's one last important distinction to notice, which is worst case and best case, right? Worst case and best case presuppose that we have already chosen the worst and best possible input. We then conduct analysis on the function, assuming that the inputs are already fixed. And what this means is that when you see the words worst case and best case on a test or on a CSM worksheet, you always want to answer in theta bound, right? Here is the explanation as to why, right? Because we have presupposed this, there's nothing else that we could change about the function in order to make the O and omega bounds different, right? And so therefore, they're always going to convert to a theta bound. This is a bit abstract, so let's bring this into a concrete example to understand what our thought process is. Let's look at this top function, which is find x. We're given an integer array A and an integer x that we want to find in this array. And so we're going to iterate through this array A until we find a value which matches x, and then we terminate our function, right? We've seen examples of this function before, and we know that it has an O bound of n and omega of 1, right? But if you wanted to ask us what the worst, the best case possible, the best case scenario, then we presuppose that x is already in the best case. Like, for example, if we wanted to put it in very concrete terms, if you look at the second function, we literally define x as equal to a of 0, right? The runtime of this function does not depend on the length of a at all. It has a theta bound, right? Because no matter what a is, into x is always a of 0, and this function will always terminate in constant time. And so we say that the best case scenario has a runtime of theta 1 in this instance, and an overall worst case and best case, at least for the purposes of this class, are always going to be answered in theta. All right, now let's work on the question itself. Part 1. In the worst case, how long does it take to get to the nth element of a single linked list? All right, now that you guys have thought about it for a bit, the first thing that we have to do is look at it as a singly linked list and understand how we might implement this function, right? Singly linked list gives us a couple things. It gives an int node, which is a sentinel that points to the first int node in our list. We also understand how int node works, which is exactly like a linked list in CS61A, as well as integer signs, right? And so how would we implement getting the nth element of a singly linked list? Well, we can't just go in and choose the nth element, right? In order to get the nth element, we're going to have to implement a for loop, which iterates n times using sentinel.next, and it's going to return that value. And what we realize quickly that this function is going to have a runtime of what? Well, notice first of all that the worst case is asking us specifically for the worst case. And so know that you have to answer this in theta, right? And the theta bound for this particular one is going to be theta n, because it's going to run corresponding to n, right? Now we're going to look at this question, which is in the worst case, how long does it take to get the nth element of an array? All right, so once again, we are working with worst case, so we want to answer using theta. And now let's look at our implementation, right? An array is very useful because it allows us to access whatever the index is. We can just simply return array of n. And so this has a runtime of theta 1. Next up, in the worst case, how long does it take to insert into a linked list? Take a moment to think about this for yourself. All right. And okay, let's kind of walk through it step by step. What does it take to insert into a linked list? Well, you need to set the previous node to have its next equal to the new node we created. And we need to set the new node we created dot next equal to the next node in this line, right? And so because a singly linked list only gives us access to whatever is next, it doesn't have any access to what goes previously. And so therefore, in order to insert into a list, a singly linked list, we have to iterate through the singly linked list until we find the place that we want to insert it. And then we use the node there and the node before it, right? And so therefore, an implementation might look something like this, right? Where we have a tracker node, which is equal to sentinel, and then we iterate slowly through n. And then we create a new node, right? New node.next equals tracker.next and tracker.next equals new node. And this is, we like place it in the middle between the tracker and tracker.next. We just place it in the middle here. Right? And so this has, once again, worst case, runtime of theta. Now let's take a look at a kind of tricky conceptual question, right? Assuming there's space, what are the runtime bounds of putting an element in an array, right? Well, I mean, this part is at least slightly simple, right? We insert at n, where we're given this integer n that we know is not obstructing any value that already exists, and we want to put in a value. And so we just do array of n equals value, right? And this runs at a runtime of theta 1. However, if there's no space left in the array, and we still want to retain all the information that's already in the array, well, if we wanted to insert something in there, well, we physically cannot, right? Because the array is already completely full. We can't put more information into it. And in that case, we're going to need to resize our array. Now, unfortunately, the code is a bit long, but let's kind of think through what resizing an array would look like and how long that would run for. Well, in order to access every single integer, every single value in the array, we're going to have to go step by step and iterate through the length of the array, right? And copy it into a new array that is larger, then input our new value into that larger array. And so the iterating through every value in our current array step is going to take n time. And so therefore we say that this runtime is theta n. All right. All right, I forgot to put the animation here to make this appear later, but we're just going to roll with it. How would knowing the size of our data structure in advance impact our decision to use linked lists or arrays in a hash table? All right, this is an interesting question. The answer is, if you know in advance, I mean, based on what we looked at previously in this question, right? Generally, if you already know how large a data structure is, then arrays are going to be more efficient because of two factors. Arrays allow you to add and access items in constant time, right? And if we're not adding anything else, and if we're not like, if we don't have to add more values to this because we already know the size, right? We don't have to ever resize array, which is the inefficient part of array. However, linked lists might definitely be more useful in different contexts. For one, linked lists are more memory efficient, right? If you think about it, like if you have an array and you are only using like half of the elements in the array, half the rest of the array still has to exist in memory somewhere, right? And that's very inefficient. However, a linked list, when you add things to a linked list, it just like creates it one by one as it is needed. And when you remove from a linked list, the previous nodes are deleted, right? And so it is very, very memory efficient to use a linked list. Also, expanding arrays is less efficient than expanding linked lists. And so in a situation where you don't know what the final size of your array is, the final size of your data set, and you are considering that maybe in the future we're going to have to add a lot more, then using linked lists might be a better choice. And overall, that is it for question 3. Thank you so much for watching.